Your FastMCP tools work perfectly in development, but suddenly fail in production when the MCP session isn't fully established yet. We'll handle this edge case by building a session-aware tool that gracefully falls back to HTTP request data when the MCP context isn't available, ensuring reliable behavior in all environments. You'll see exactly how to check for session availability and safely access request metadata regardless of the transport layer.
From FastMCP, import FastMCP. Context. From FastMCP server dependencies, import get HTTP request. MCP equals FastMCP. Name equals session-aware DEM. At MCP, tool. Async def session info CTX. Context. Dict. Returns session information when available. Hash check if MCP session is available. If CTX, request context. Hash MCP session available. Can access MCP-specific attributes. Return. Sessionid, CTX session ID. Requested, CTX request ID. Has meta, CTX request context. Meta is not none. LC. Hash MCP session, not available, use HTTP helpers for request data. If using HTTP transport. Request equals get HTTP request. Return. Message, MCP session not available. User agent, request headers get, user agent, unknown.
This demonstrates the context injection pattern for handling request-aware operations in RPC frameworks. The context object acts as an implicit dependency container, providing access to request metadata, session state, and framework capabilities without polluting function signatures with transport-specific parameters. What makes this distinctive is its ability to bridge the gap between stateless function design and stateful request processing. The pattern works by leveraging Python's type hints for dependency injection, where the framework automatically supplies the context object when needed. This creates a clean separation between your business logic and infrastructure concerns, allowing functions to remain pure while still accessing request-specific data like session IDs, headers, or progress reporting capabilities. The context itself is request-scoped, ensuring isolation between concurrent operations. This approach solves the common problem of how do I access request data without making my functions framework-specific. It's particularly valuable in RPC systems where you need to maintain clean function interfaces while still handling real-world concerns like authentication, progress tracking, or client metadata. The trade-off is that your functions become implicitly coupled to the framework's context system, but this is generally preferable to explicit coupling through parameter passing or global state. Let's break it down line by line.
From FastMCP, import FastMCP. Context.
Imports FastMCP, the core class for creating AI-callable tools, and context, which provides session metadata and logging capabilities. These are the foundational components for building session-aware MCP tools that can track requests and maintain state.
From FastMCP server dependencies, import get HTTP request.
This imports the HTTP request helper from FastMCP's server utilities. It provides fallback request access when the tool isn't called through an MCP session, like during direct HTTP invocations. This enables hybrid operation across different transport protocols.
MCP equals FastMCP. Name equals session-aware DEM.
Instantiates the FastMCP server with a human-readable name for debugging and logging. This is the entry point for all tool registration and request handling, serving as the core controller for your AI-callable functions. The name appears in logs and error messages, making it easier to trace issues in multi-service environments.
At MCP, tool. Async def session info CTX, context, dict. Return session information when available.
This defines an AI callable tool using FastMCP's decorator pattern. The CTX context parameter provides session and request metadata, while the return type hint, dict, automatically generates the tool's schema. All FastMCP tools follow this signature for consistent AI integration.
Hash check if MCP session is available. If CTX, request context.
This checks for an active MCP session by verifying the request context attribute. FastMCP populates this when the tool is called through an MCP session, distinguishing it from direct HTTP calls or other transports. The pattern enables session-aware behavior while maintaining compatibility with non-MCP invocation methods.
Hash MCP session available. Can access MCP-specific attributes. Return.
This branch handles the MCP session available case, returning a dictionary of session-specific metadata. The session ID, requested, and metadata availability are critical for debugging and request tracing in distributed systems. All FastMCP tools should follow this pattern. Check CTX. Request context first, then fall back to transport-specific helpers.
Session ID, CTX session ID.
This extracts the unique session identifier from the FastMCP context. Session IDs track individual user interactions across multiple tool calls, enabling stateful conversations with AI models.
Requested, CTX request ID.
This returns the unique request identifier from the FastMCP context, enabling traceability across distributed calls. Critical for debugging and logging, it links individual requests to their execution flow.
Has meta, CTX request context, meta is not none.
This checks if the MCP request contains metadata. The meta field stores additional context like user preferences or authentication data, and this Boolean indicates whether any metadata exists for the current session. Closing brace for the conditional block terminates the MCP session available branch, ensuring clean separation from the fallback HTTP request handling.
Else.
This else branch handles the fallback case when no MCP session exists. It demonstrates defensive programming by providing meaningful output even when the primary session context is unavailable, ensuring the tool remains functional in different environments. The pattern shows how FastMCP tools should gracefully degrade when session-specific features aren't available.
Hash MCP session, not available, use HTTP helpers for request data. If using HTTP transport. Request equals get HTTP request.
This handles the fallback case when no MCP session exists. The get HTTP request helper extracts raw HTTP request data, enabling basic request inspection even without a full MCP context. This maintains functionality across different transport layers.
Return.
This begins returning a dictionary response, the standard pattern for FastMCP tool outputs. Structured return values ensure consistent serialization for AI model consumption, while maintaining human readability for debugging.
Message, MCP session not available.
This provides user feedback when the MCP session is unavailable. The clear message helps distinguish between session-backed and HTTP-only requests, aiding debugging.
User agent, request headers get, user agent, unknown.
This extracts the user agent header from the HTTP request, falling back to unknown if missing. It demonstrates defensive programming for HTTP metadata access, ensuring the function always returns a valid string even when headers are incomplete. The get pattern with default value prevents key error exceptions in production. This closing brace terminates the conditional block that handles MCP session availability. It cleanly separates the two distinct response paths, one for MCP sessions with full context and another for HTTP fallback scenarios. The structure ensures proper scoping and prevents logic leakage between the two cases. Contextual session awareness. FastMCP tools dynamically adapt between session-bound and sessionless execution, using the context object to detect available runtime information. The request context property is none when no MCP session exists, forcing fallback to HTTP transport helpers. Always check CTX. Request context before accessing session-specific attributes like meta or sessionid.
The context that knows everything knows nothing until asked.